So hello everyone, we are waiting for Professor Sudeep to start the sessions. Kindly wait for some time. And also I have started recording this session, so I guess you don't have any obligation on recording this session. Yeah, thank you.
To hear. Yes, I have joined. My voice is audible to you.
Yes, sir, it's audible.
Okay, all right.
Yeah, am I audible? Hello?
Yes, yes.
Yes, sir.
Okay, okay. Yeah, thank you, thank you. Actually, there is some network issue in my office, so I have to log in from my mobile. Extremely sorry for this inconvenience. Professor Umesh Chandrapati, head of the department, acting head of the department of Electronics and Communication Engineering, NIT Rourkela, already has joined the meeting. So, sir, shall we start the formal inaugural session?
Yes, yes, we can start.
Okay. Thank you. So, good evening, everyone. On behalf of the organizing committee, I am delighted to welcome you all to this 4-day online workshop on Metaheuristics, a class of intelligent search methods in AI, organized by Department of Electronics and Communication Engineering, NIT Rourkela, in association with IEEE Student Chapter Rourkela subsection. First and foremost, I would like to express my sincere gratitude to our head of the department and the director of NIT Rourkela, Professor K. Umesh Maheshwar Rao, for allowing us to conduct such a great workshop. I am also thankful to Chair IEEE Rourkela subsection, Professor Dipti Patra, for accepting our request to be part of the technical co-sponsor of this workshop. Further, I extend my thanks to the speaker, Mr. Shubham Kesari, a Prime Minister Research Fellow at IIT Kanpur, for accepting our request to deliver the lectures as well as to conduct the hands-on sessions in this 4-day workshop. Mr. Kesari is a PhD scholar, PMRF fellow in the Department of Management Science, Indian Institute of Technology, Kanpur, under the supervision of Dr. Abhijit Khanra. His PhD work comes under the broad area of production scheduling. He completed his BTech in Mechanical Engineering from National Institute of Technology, Durgapur in 2019. During his time, he got the opportunity to do an internship at European Council for Nuclear Research, which is commonly known as CERN, Geneva, Switzerland. There he worked on quality assurance of the gas electron multipliers foils for upgrade of the a large ion collider experiment time projection chamber, which is known as ALICE TPC. He has also worked in L&T construction for more than a year and resigned as senior engineer. Mr. Kesri has a proven track record of delivering successful workshops, including Foundation of Artificial Intelligence using Python at Institute of Smart Structure and System India, which is commonly referred as IEEE India. An introduction to game theory at National Program on Technology Enhanced Learning, which is referred as NPTEL, data science with Python and introduction to ML at the Department of ECE, University Institute of Engineering and Technology, CSJM, University Kanpur. I have witnessed his exceptional work ethics and dynamism. I am sure you will find all the sessions engaging and enjoyable. A classroom without a student is purposeless. A library without books is meaningless. A stage without performers is lifeless. Similarly, a workshop without participants is pointless. As the coordinator of this workshop, I am thrilled to see the diverse range of participants from academia, industry, and research institutions. In this workshop, total 185 participants have registered, out of which 40 participants are from bachelor program like BBA, BTech, or BS. 30 participants are from master's program like MTech, MBA, MS. 75 participants are from PhD. Rest 40 participants are working professionals like assistant professor, professors, scientists, or researchers from different organizations. The participants are from various academic premier institutes like IIT Bombay, IIT Kharagpur, IIT Kanpur, IIT Rourkela, IIT Dhanbad, NIT Rourkela, IIM Ahmedabad, IIM Lucknow, IIM Bodh Gaya, National Institute of Fashion Technology, University College London, Georgia Tech, Purdue University, and the list goes on. Also, we have working professionals from Symphony AI, Kenview, Freelance, VSL India Private Limited, Indian Army, Green Swans, and so on. We are really thankful to all of you for your overwhelming response to take part in this workshop. Your presence is a testament to the growing interest in Metaheuristic and their application in AI. This workshop aims to provide a platform for knowledge sharing, collaboration, and networking among experts and enthusiasts in the field of metaheuristic. As we navigate the complex landscape of AI, metaheuristic have emerged as a powerful tool for solving optimization problems, improving decision making, and enhancing intelligent systems. This workshop is designed to explore the vast potential of metaheuristic and their application in AI. So let us embark on this intellectual journey together, exploring the fascinating world of metaheuristics and their application in AI. Thank you, everyone, and let's make this workshop a memorable experience. Thanks again. With this, I am concluding my notes, and I request Professor Umesh Chandra Poti to share a few words with regarding this. Professor Umesh Chandra Poti is a pioneer researcher in NIT Rourkela. He is working on computer vision. So he is one of the most suited person to explore the requirement of such workshop and direct hands-on session. We have kept this workshop after office hour so that we all can attend this. So many professionals are there who can attend this workshop. So it is becoming hectic. I know from the morning our schedule starts, but from 5:30 to 8 we have to attend. But it is beyond the office hours, so we can complete it. Okay, Professor Poti, if you can share your views. Thank you, sir.
Thank you very much for a nice introduction, Professor Kundu. Coordinators, Professor Sudeep Kundu and Professor Sagat Kumar Kaur, speaker, Mr. Shubham Kesari, and participants. Good evening to all of you. In fact, as the head of the department, I should introduce something about our department itself. This Electronics and Communication Engineering Department in NIT Rourkela was established with a vision to make it an acclaimed department internationally as well as nationally. So the emphasis is on research and teaching. Very high quality students, in fact, join this stream with high ranks. Wherever possible, they opt for this branch. Our department has two BTech streams, Electronics and Communication Engineering. Second one is Electronics and Instrumentation Engineering. In addition to that, it has 5 specializations: Communication and Networks, Electronics and Instrumentation Engineering, VLSI and Embedded Systems, Signal and Image Processing, and finally, Microwave and Radar Engineering. In addition to that, we have a lot of PhD students who are pursuing in their goal. And we have also investigating many of these government-sponsored projects sponsored by DRDO, ISRO, DBT, etc. Coming to the this particular 4-day workshop, that is Metaheuristics, a class of intelligent search methods in AI. Professor Kundu has given an introduction on this. I also agree 100% that this is a very state-of-the-art topic in which a workshop should be conducted. Particularly, Metaheuristic is a set of optimization algorithms, those who are designed to solve complex problems, which is not possible by traditional methods. In fact, these enhance the performance and augment the capabilities of AI systems. It has got a wide domain of applications. In fact, it is an iterative technique. It goes on searching for an optimal solution, may not be the best one. So, in fact, due to the recent developments, many complex engineering problems are getting solved by these metaheuristic approaches. And coming over here, it has also some challenges. That means exactly it is difficult to know where to stop this iteration to get the best optimal solution. And also, second one, it is computationally expensive. So sometimes it is difficult to apply this in real-world, real-time problems. But still, nevertheless, with this shortcomings also, it has got an ideal tool to solve the complex problems, which, as I have told, which is not possible by traditional methods. Then, in fact, the course content, what you can see, it is very up to date, and it has also hands-on training also. By one has to see the Python programming also. So with this 4 days of work, so one will have enough graphs over this interesting topic. And as Professor Kundu introduced, Mr. Shubham Kesari has got a wide experience in handling this type of workshop. I'm pretty sure that when you complete the workshop, you'll be satisfied that the time invested has given me enough experience, enough knowledge to add in my research or to handle other complex problems. So I understand that you'll enrich a lot out of this 4-year experience. Thank you very much and hope for a rich experience professionally. Thank you all.
Thank you very much, sir, for your so nice introduction and 50% technical session, iteration, metaheuristics, how it goes, convergence. So thank you very much for your so nice introduction. So we shall, yes, sir. So we shall start the session. Mr. Shubham, are you ready to start now, or we shall
Yes,
have
sir. I am ready to start now, so we can take a break after some time.
Okay, sure. So let us start the session now itself. I request all the participants, see, your mic has not been forcefully muted. The reason, so that flexibility will be there, but try to keep your mic mute. At the end, you raise your hand and we can have the interactive session with Mr. Kesri. But till that time, please, our request is please keep your mic off. Thank you. Okay, Mr. Shubham, you can start your session.
Thank you, Professor Kundu. Thank you, Professor Umesh, for your kind words. So I will like to introduce myself with the start of the workshop, and then we'll proceed a little bit. And one small correction, I have not done a workshop in NPTEL. I was a teaching assistant at a course in NPTEL. So yeah, small correction. Yeah, thank you so much. So I'll just share my screen and then we'll begin. And so one small note, you will not be able to have chat option in your end. So if you want to communicate with me, please try to communicate using the WhatsApp group. From time to time, I'll stop in between and I'll ask you to ask questions, and then we'll try to solve the queries which you have. I have kept this workshop from the basics. So today we will only talk about some basics of optimization and some techniques which are used to solve search problems. Specifically optimization problems, and then we will proceed to see how metaheuristics are used, which kind of metaheuristics are used, their classification, and so on and so forth. So spare me a minute. Okay, so this workshop is titled Metaheuristics, a class of intelligent search methods in AI. So we will talk about metaheuristics and what they are. Before that, this second line where I have mentioned a class of intelligent search methods in AI. So AI is a very broad topic, and there are many different methods to perform search. So there are different kinds of methods to perform search. Metaheuristics falls under this search methods in AI. So it is a class of search methods. In this workshop, we'll mainly focus on metaheuristics and not on AI. Okay, so the focus of this workshop will be on the building blocks of metaheuristics. You will understand what are the building blocks of metaheuristics and then their implementation. Okay, so today's session is all about introduction to optimization. So I'm Shubham Keshri, a PhD scholar at the Department of Management Sciences, IIT Kanpur. And this workshop is presented as a PMRF teaching duty organized by the Department of Electronics and Communication, NIT Rourkela, in association with IEEE student chapter Rourkela subsection. Okay, so these are the contents of today's workshop. It will not be wise for me to go through this content because This is the first slide I'm showing you. So let us proceed, and from time to time, if I need, I'll come back here, or we will see. Yeah, okay. So this is the workshop schedule. So the workshop is arranged for 4 days, 2 hours for the first 2 days and 3 hours for the next 2 days. And these are the contents of this workshop. So in today we will talk about introduction to optimization, some basics of optimization, what is optimization, what is different search spaces, what is an objective space, what kind of methods which are used to solve optimization problems, like the categorization of exact methods and approximate methods. Then we'll briefly talk about linear and integer programming. We will not go into depth of linear and integer programming, and then we'll proceed to introduce what a heuristics is and what a metaheuristics is. We will see what greedy algorithms are used to solve some prominent problems in this field. And I have also kept solution representation in these slides. If we get time, we will cover that. Otherwise, we'll keep it for the next day. So from tomorrow, we will begin with the first class of metaheuristics, which are known as single solution based metaheuristics. And we will cover local search, simulated annealing, and taboo search. And we will have a session on the implementation of either one or two of the heuristics depending upon time. And on the last day, we will talk about population based metaheuristics. A popular algorithm is genetic algorithm, but there are many more algorithms. And I have kept ant colony optimization here, but the time will govern whether we'll be able to go into ant colony optimization or not. Nevertheless, we'll have a hands-on session which will help us get the implementation details of these kind of algorithms, and we will see implementation of genetic algorithm. Okay, so this is the plan of this workshop divided over 4 days. All right. And for each day, we will have a 5 to 10 minutes break so that you can go for a water break or something. Yeah. So yeah, we'll proceed. All the workshop materials will be provided to you. So this is a website which I have created where you will get the recordings of this workshop as well as the slides which I am using. So you don't need to email me for the contents. And this reference book by Talbi, Metaheuristics from Design to Implementation, is the book I'll follow for this workshop. So everything that I'm teaching in this workshop has been taken in some form or the other from this book. And yeah, some course which I have done with my supervisor, a blend of all these things are presented in this workshop, but mainly this book will be followed. This book is available in the internet. You can download it. Yeah, and please note that this meeting doesn't support chat option. So please take 5 minutes. If you have not joined the WhatsApp group, kindly join the WhatsApp group. The link to the WhatsApp group has been sent to you via mail, and you can communicate with me using that WhatsApp group in this live session. Okay, I'll allow for some participants to unmute and speak, but not in between the sessions because there are a lot of participants and it may become chaotic. Okay. So yeah, I have introduced myself and this is my website. You can visit my website to see more details. And yeah, you may ask me why a BTech student, a BTech graduate is taking a workshop on metaheuristics. So I completed my BTech in 2019. After that, I was in L&T construction for a while, but I joined IIT Kanpur as a PhD student, and I have also completed the requirement of master's degree at IIT Kanpur. So I have not availed the master's degree, MTech degree, but yeah, I have qualified all the requirements for master's degree. So I hold a master's degree. I don't hold a master's degree, but I have completed the requirement for master's degree. This is my email ID. You can mail me anytime. I might take 1 or 2 days to reply, but yeah, I will try to reply to the mails of your mails, right? So what is the flow of today's session? So what I have done is, instead of introducing some concepts at the beginning of the session, we will see some problems. Through that problem, so not 1 or 2 problems, maybe 4 or 5 problems, and through that problems, we will introduce the concepts which we are trying to build in this session. Okay, basically introduction to optimization, what an optimization problem is, and so on and so forth. So this is the first slide of this session where I'm asking you a question. You can raise your hand. There is a raise hand button in your meeting end. And the question is, have you ever done mathematical modeling before? So take a minute. You can raise your hand. And I'll just see the count, how many of you are raising your hand. Right, so out of 88 participants, I guess around 15 or 16 people are raising their hands. Okay, so I guess I want to change this idea. So many of you are thinking that they have not done mathematical modeling before, but my next slide will show you that indeed you have done mathematical modeling. Okay, so we'll see the next slide. So that was the idea. Okay, so the next problem which I have posed in this slide is a very simple problem which we have done in mathematics in our high school. A father's age is 4 times as that of his son, and in 10 years the father will be twice as old as his son. How many of you have done this kind of problems before in high school? I guess most of you will raise your hand, right? And when you write this problem in terms of mathematical equations, it becomes a mathematical model. So indeed, we have done mathematical modeling. We were not introduced to the term mathematical model before, or maybe we were introduced, we did not pay attention that this indeed is a mathematical model. Okay. So the problem again, I'll repeat the problem, or I'll read the problem again. A father is 4 times as old as his son. In 10 years, the father will be twice as old as his son. The question is, what are their current age? Okay. So let us try to again write the mathematical model for this problem, or formulate it as a mathematical model. Okay, so what can be done? You can try at your end. I will also help you proceed. Okay, so let us assume some variables. So we'll say the son's age is X and father's age is Y. So the first line says a father is 4 times as old as his son. By the way, when I write son X, father Y, this is not an appropriate way to write. We have to write it appropriately. So X represents the age of son, Y represents the age of father. These little things will become important when you move forward with this kind in this field, or not in this field in general, because it will define that variable very appropriately. So for the time being, just for sake of presentation, I am writing X represents the age of the son and Y represents the age of father. Okay. So the first equation says that Y is equals to 4X. A father is 4 times as old as his son at present. Okay. The second line says in 10 years, the father will become twice as old as his son. So in 10 years, father's age will be Y plus 10 and son's age will be X plus 10. And it says in 10 years, father's age will be twice as old as his son. So these are the two equations which we get from this problem. And we are asked to solve this problem for the value of X and Y. Okay, so this is the problem. That is what I have written here. Let X be the son's current age and Y be the father's current age. And then we write this problem and then we solve this problem simultaneously to get the value of X and Y. So this is a basic mathematical model that represents the relationship between the father and son's age using algebraic equation. So this is indeed a mathematical model. Okay. And just for the sake of completeness, I have solved this two equations. Frankly speaking, it was not necessary to solve that problem, but for the sake of completeness, I have done it. So the son's age comes out to be 5 years. And if it is in years and Y represents the father's age, it comes out to be 20 years. Okay. This is a second kind of problem. Okay. So in this first problem, notice that we have only obtained one solution. X is 5 and Y is 20. So this is the only equation which satisfies the two equation. This is the only value or the solution which satisfies the two equation. Okay. This is another problem, budget allocation problem. So there is a student. So someone is unmute. If you want to speak, you can speak or kindly mute yourself. Okay. So there is a student who has a budget of 200 rupees and he wants to buy pen and notebook. So a pen cost 10 rupees each and a notebook cost 25 rupees each. And the budget is 200 rupees. Okay. And we will come to this. We will come to this line. So what we will do, we'll do the same thing which we did for the previous problem. We will say, let the price of pen is X and the price of notebook is Y. So price is X and price of a notebook is Y. So the budget, we have a restriction. So there is some kind of, so it is a technical term, constraint. So there is a constraint on budget. So what is the constraint? 10 times X. That is, if X represents, okay, it's not price, it's quantity. I'm sorry. If X represents the quantity of pen purchased and Y represents the quantity of notebook purchased. So total price of pens will be 10 times X, because 10 is the price of unit price of the pen and X is the quantity of pen purchased. So we'll have 10 times X plus 25 times Y, right? 25 is the unit price of a notebook and Y is the number of notebook purchased. This value shouldn't be more than 200. So we have to write like this. 10X plus 25Y is less than equal to 200. This is also a mathematical, not equation in technical terms, it is an inequality. Nevertheless, it is a constraint. It restricts the amount of money you can spend on pen and notebook. Okay, so we have written the constraints. Now, before coming to this, whatever I have written next, you can see that this equation satisfies many values of X and Y. X can be 0 and Y can be 1. X can be 10 and Y can be 0, and so on and so forth. Many values satisfies this constraint. Again, I'm using this term constraint. I have not defined it properly, but it means restriction. Okay. So there are many values which satisfies this constraint. This is a thing you should notice. Okay. Now, the question is, the student wants to buy maximum number of items. So what is the total number of items the student purchases? The total items are Y plus X, right? X is the quantity of pen and Y is the quantity of notebook. So the total item purchased is X plus Y. So the complete mathematical model will become maximize X plus Y such that, or subject to, whatever you say, such that or subject to the constraint 10X plus 25Y is less than equals to 200. And there are two more constraints. X should be greater than equals to 0 and Y should be greater than equals to 0. Obviously, you cannot buy negative number of pens and negative number of notebooks. So this is again a mathematical model, right? And you see, there are many values which satisfies this constraint, but there's an objective to fulfill. What is the objective? You have to maximize the number of items purchased. The quantity of items purchased, summing both up, should be maximized. So this is also a mathematical problem where there are many feasible solutions. What is a feasible solution? Again, this is a technical term. I'm not defining it appropriately, but in layman terms, it means a solution which satisfies the constraint is a feasible solution. Okay. Yes. Okay. So a solution of these inequalities which satisfies these inequalities is known as a feasible solution. So there are many feasible solutions to this problem. And among these feasible solutions, you have to find that feasible solution which maximize the objective function. So this is again a technical term, objective function. Okay. So I'll repeat everything what I have said again. This is a mathematical model which have some constraints. There are more than one solution which satisfies the constraint, and these solutions are known as feasible solutions. Among these feasible solutions, we are trying to find that feasible solution which maximizes, because it is a maximization problem, which maximizes the objective function. What is the objective function? The thing we are interested in. So it is a very loose way to define objective function, but yeah, I guess you know, get the idea. So this is the objective function. Okay. So this is again a mathematical model. You can put your hands down. If you have doubt, you can raise, then I'll know the doubt is right now. Okay. All right. So again, I have written the same thing. X represents the number of pen, Y represents the number of notebook. This is the budget constraint. These are known as non-negativity constraint. And this is the objective function. Okay. And just for sake of completeness, I have not solved the problem, but I have given some idea of how to solve this problem. What I'm doing is I'm taking values. So I'm saying X is equals to 10 and Y is equals to 4. Let us see if this satisfies the constraint or not. So when I put it in numbers, so what is the constraint? 10x plus 25y has to be less than equals to 200. This is the constraint. And obviously there are two more constraints. X is greater than equals to 0 and y is greater than equals to 0. So when I'm taking 10 and 4, these two constraints are automatically satisfied. We have to check for this constraint. So you see 10 times 10 plus 25 times 4 comes out to be 200. And it satisfies the constraint. So this is a feasible solution to this problem. And what is the objective function of this feasible solution? It comes out to be 14. 10 plus 4, 14. There can be another feasible solution. X is equals to 5 and y is equals to 6. And we see that this is also a feasible solution to this problem. And the objective function comes out to be 11. Again, I list down X is equals to 10 and Y is equals to 6. And I see it exceeds the budget. So this is not a feasible solution to this problem. Okay. So you see, this is one approach you can take to solve this problem. I'm not talking about whether it is a good approach or a bad approach, but this is an approach to solve this problem. We're trying to plug in some values and we are trying to see what is the objective function. And among these three values, 1, 2, and 3, among these three values which we have checked, we can see that the first value performs better. It gives me an objective function of 14. I don't know if it is the best I can have or not. Maybe there is a value 15, 16, 17, I don't know. But among the few which I have tried, I saw that the first one performs better. Among the ones which I have seen, the first one performs better. So this is an approach to solve this problem. And meta-heuristics in some way or the other, not exactly, but in some way or the other tries to do the same thing. It tries to obtain some solutions. It plugs in the number and check what is the objective function. And among all the solutions it has, it will give you the best solution it has found so far. It doesn't know whether it is the best or not. Why? Because to tell that it is the best solution, you have to exhaust all possible solutions. And when you have exhausted all possible solutions, then only you'll be able to say, okay, this is the best solution. And meta-heuristics doesn't aim to exhaust all possible solutions. The idea is we will explore few solutions. It's again, these are in quotes, not few, and not technically, but as compared to exhausting all solutions, few solutions. Okay, so search few solutions, and among those few solutions, this is the best I have obtained. Okay, and again, note one thing. These are search problems. We are searching for a solution among a set of solutions. Okay, so these are search problems. In the name of the workshop, we have a class of intelligent search methods. So these are search problems. So meta-heuristics are applied, not technically, but yeah, we apply it to search problems to find a solution to a problem. Okay, so this is, till now we have talked about mathematical modeling and a very crude approach to solve a given problem. Now I see two hands up. Do you want to ask any questions? Okay, so if not, kindly please put your hands down. If you have any questions, you can put it up again. Okay. Okay, so we have, sorry, yes. Okay, so we have seen what a mathematical model is, not technically, in just an example of a mathematical model. Now we'll move on to another kind of model, and I'll not name the model, but we'll see one example again. So this is known as a diagram tracing problem, and I'm pretty sure you have done it when you were a child. The problem is trace the diagram. Someone is unmute. Can I know if you have any query? Okay, so I'm assuming there is no query. The problem is trace the diagram without lifting, without taking the pen off the paper, and without going over the same line twice. So this is a very basic problem which we used to do as a child. You can take a minute or two to try and solve this problem, and then we will see some implications or maybe some concepts through that. Okay, take a minute and try. So Professor Sudeep, I'm not able to read the chat. If there is some query in the chat, you can just pause me and let me read the question. Okay.
Yeah, yes, sure, definitely I shall ask at the convenience, but till now no queries.
Thank you. Thank you. Okay, so I guess you must have tried to solve this problem. I'll show you one solution or maybe two solutions to this problem. Okay, so maybe we can start from this point and we'll go up and we can go this side, then again this side. We can go here, then here, then here, then here, and then here. So you see, I have not lifted the pen off the paper, and I have also not traced a line twice. So this is one solution to this problem. What I have done is I have started here and moved like this. Okay, did I move like this? No, I moved this way. Okay, so this is one solution to this problem. I'll show you one more solution, but this is not the thing which I want to take away from this slide. Okay, but nevertheless, let me show one more solution to this problem. So you get the idea. These are few solutions which I have shown in this paper. But you see, what was the method we were using to solve this problem? It was a brute force method. Again, this is also a technical term, brute force method. What does it mean? We are trying to solve this problem using the approach you can in non-technical terms, you can call it hit and trial method. You're trying something, and if you see it doesn't work, you scratch that thing and you start again. So maybe you started like this, and this, and you got stuck. So okay, this I didn't get stuck, but maybe you were trying something and you got stuck. So this is known as a brute force method, where you are trying to solve the problem using one solution at a time. The way we were trying to solve this problem, we are trying to get one solution, checking if it is satisfying the constraints or not. And again, we are trying to get one more solution, checking if it is satisfying the constraint or not. So you see, in this problem, there is constraint. What is the constraint? You cannot lift the pencil off the paper. This is one constraint. And the another constraint to this problem is you are not allowed to retrace your path. These are two constraints to this problem. And I'll give you more examples to make you realize that this problem is applicable in real life. This may seem a very toy problem, but this problem is applicable in real life as well. Okay, so this was the first problem. Okay, before we proceed to the next problem, you see we were using hit and trial method. We were trying to get a solution. If we didn't get a solution, then we'll try another solution, and so on and so forth. So you see, this is one shape that I gave you. There can be infinite number of different shapes I can give you. I can add two more things over here, or maybe I can do multiple things with this and I can give you this problem. You see, the problem is the same. We have to trace the diagram without lifting the pen off or retracing the line again. But the basic problem remains the same, right? This diagram may change. This diagram may change, but the basic problems remain the same. So if you try to solve the same problem again and again with different diagrams, it is a waste of time. You're wasting your time using a brute force method, right? There must be a better way to solve this problem. So to solve this problem, we should take a step back and think, is there a way to inform us that it is not possible to trace this diagram with the given constraint? So my question is it possible to tell before I try to solve that problem, by seeing the problem, is there a way that I can say that it is not possible to trace the diagram? Is there a way? And if there is a way, what is the solution? So we can break this question into two parts. First, is there a possible solution to this problem or not? Second, if there is a problem, if this problem is feasible, or we can, or if it is possible to trace the diagram, what is the solution to this problem? Okay, so these two questions should come to your mind before just blindly solving this problem by doing hit and trial method. So what are the key takeaways? If we generalize this problem, instead of this problem, I can give you, so again, one technical term, this is a graph. Okay, so if I give you a general graph with maybe hundreds and hundreds of edges, so these are edges and these are nodes. Okay, so a graph is made of nodes and edges. So the thing I am telling you is, if I give you a general graph where there are hundreds and hundreds of edges and so many number of nodes, and I ask you the same question, is it possible to trace the diagram without lifting the pen or without going over the same line again? It is not possible to do using brute force method. So there has to be, or I'll not say has to be, we should try to find a way to solve that problem which is more efficient, right? So if we have, sorry. So is there, so what the question is, if I generalize this problem, can I solve this problem quickly? And the second thing is, you should note that there are multiple solutions to this problem. I gave you the example that you can trace the same diagram again and again. So these are the two takeaways from this example. Okay. Again, we'll move on to a next example. So I'm not introducing concepts. I'm just giving you problems, and using that problem later on, we'll build concepts. Okay. So this is another problem known as, so I may pronounce it incorrectly, but again, this is known as Königsberg Bridge Problem. So this Königsberg is a East Persian city, and in this city there were some land masses and there was a river which flowed through this city, across this city. Okay, so the resident of this city wondered if it is possible to take a walking tour of the town, crossing each of the 7 bridges exactly once. So there were 7 bridges in this city. So these are the land masses. Okay, these are the land masses, and there are 7 bridges. So I have labeled it 1, 2, 3, 4, 5, 6, 7. There are 7 bridges. The resident wondered if it is possible to take a walking tour of the town without crossing each of the, it has to cross all the 7 bridges, and it should do it exactly once. You cannot cross a bridge again. Okay, so this is another problem. Okay, so this is the, you can say, what I should say, a representation of the land masses and the river. I can transform this problem. You see, it has a lot of detail. This is land, this is river, sorry, this is river, this is bridge. A lot of details are there. I can remove this unnecessary detail and I can simplify this problem. I can model this problem using some technique. I'll not name that technique now. I can simplify this problem. This problem I'll simplify such that I do not focus on unnecessary detail, like this is land, this is a bridge, this is river, and so on and so forth. So what is a simplifying model? Simplified model. You see, this is a simplified model. The land masses are now made as nodes and the bridges are now made as edges. So you see, when I write 1, so this is the first bridge, this bridge. Okay, and it connects landmass A to landmass B. Landmass A to landmass B. Second bridge also connects landmass A to landmass B. Third bridge connects landmass A to landmass C. Okay, landmass A to landmass C. Fourth bridge connects landmass B to landmass C. You see, it is connecting landmass B to landmass C. Again, 7th bridge is connecting C to D. 6th is connecting A to D, and 5 is connecting A to D. So we have removed unnecessary details from this problem and we have modeled it. Now this model is known as network model. Okay, so earlier we were calling that as mathematical model. This is known as a network model. And now you see, are the two problems same? Yes, ma'am. Do you have a question? Okay, so I'll proceed. So you see, the problem, the underlying problem remains the same. I have to walk through these bridges 1, 2, 3, 4, 5, 6, 7, 8, not 8, sorry, 7, exactly once, such that I take all the bridges. So I'll read the problem again and you can take your time to read it again. The resident of the East Persian city of Königsberg wondered if it was possible to take a walking tour of the town, crossing each of the 7 bridges over the river exactly once. And this problem was solved by Euler in maybe 1739, if I remember it correctly. He gave a very elegant solution to this problem. Okay. Before that, do you see the similarity between the previous problem and this problem? Are there any similarity between the two problems? You can unmute yourself maybe. Both the
edges cannot be
repeated. Okay.
The edges cannot be repeated.
The edges cannot be repeated. Okay. One. Okay. Any other similarity?
From the same node, multiple edges.
Sorry, you are not audible clearly.
From the same node, multiple edges are.
Okay. Correct.
All the bridges have to be crossed once.
Yes, so that was said by someone else. So what were the two constraints for this problem? The first constraint is all the edges
And we have
traced, right? You cannot retrace a path, so you cannot retrace a edge. Over here also the problem is you cannot retrace or you cannot travel that bridge again, right? The second constraint for this problem was you cannot lift your pen. So you were drawing like this. Yes, and the second, what you cannot lift your pen. So you are doing like this and you cannot just from here, you cannot just lift your pen and do like this. And this constraint is also applicable to this problem. You are at landmass B, you cannot just jump to landmass D, right? You cannot just lift your pen from landmass B and then land in landmass D. You have to take one bridge, right? So you cannot trace one bridge again and you cannot jump from one landmass to the other. So both the problems are exactly the same. Exactly the same. Right? Exactly the same. Again, I'll note exactly the same. If you remove the details, we have simplified the problem. We have modeled it using mathematical model, right? And then these two problems becomes the same. Any doubt? So this is the power of modeling. When you model a problem, you get rid of unnecessary detail and you focus on the problem which you have. It may not represent the reality appropriately. You may also have to make some simplifying assumptions. Those assumptions may be correct. Those assumptions may not be correct. But at the end, if the solution which you obtain works, then it's fine. It works. Okay. Any doubt? All right, so I'll proceed. Again, so I have kept many problems first. If you are getting confused, please let me know, I'll move forward. But these are interesting problems and we'll use some of these problems going forward, okay? So this is known as Chinese Postman Problem. Read the problem carefully. The problem says, a Chinese postman wishes to travel along every road in a city in order to deliver letters with the least possible distance. So there is a city and these are turns in the city, right? These are turns in the city and these are lanes. These are lanes. The postman has to deliver letters in the houses beside these lanes, right? There are houses beside these lanes. And this postman has to deliver letters in these houses. And he has to travel all the lanes. That is one constraint. He has to travel all the lanes, right? Every road in the city. He has to travel along every road in the city. What is the least possible distance? So the question, so the problem is a little bit changed. Earlier, we were asking whether it is possible to cross all the lanes I'm again using, it was bridge, but I'm saying lanes. Earlier the question was, you have to cross all the lanes. So that is same, you have to cross all the lanes. The second was, you cannot retrace a lane. That constraint is not here. You see, he can retrace a lane back, but one objective function comes here. What is the objective function? The total distance he has traveled should be minimized. Okay, so I'll again repeat the problem again. So this problem has slight difference from the problem which we saw just now. The problem says, this postman has to travel all the lanes. He may retrace a lane back, but he has to do it using that path which minimizes the distance he travels. Now you may ask me, why do we need to retrace a lane? Retracing a lane will increase the distance. You see, there are some graphs where it is not possible to trace all the edges, right? If it is not possible to trace all the edges exactly once without lifting your pen, you have to retrace one of the path and then complete the tour. Okay. In that case, that constraint is relaxed. You can retrace a path back. There is an objective function to this problem. You have to minimize the distance he is traveling. Is the problem clear? I assume it is clear. Okay. So I have mentioned, I wanted to ask the difference between this problem and the previous problem, but I have mentioned the difference to you. First difference is you can retrace a lane back. Second is there is an objective function to this problem and you are trying to minimize the objective function. Okay. These are the two distance. When solving this problem, you can think of it as 3 steps solution approach. The first is, what are the decision alternatives? That is, what are the paths he can take to solve this problem? There can be many paths in this town. Those are known as decision alternatives. There are many decision alternatives and he can take any one. So if you go back to the problem when we are talking about budget, there are many solutions to this problem, many feasible solutions to this problem. Okay. So similarly, there are many decision alternatives to this problem. There are some restrictions to this problem. What are the restrictions? That he cannot jump from one lane to the other. He has to go via a lane. He cannot just jump. That is a restriction to this problem. And what is an appropriate objective function for this problem? The objective function is to minimize the distance he is traveling. Okay. And this objective function can be evaluated using the different alternatives. There can be one route, there can be another route, there can be another multiple routes. And for all those routes, you have to obtain the objective function, and then you can select that this is the best I have seen so far. So let us go with this, or something like that. So you see, in the mathematical model as well as in network diagrams, I have given you one crude algorithm to solve a problem. We can try different solutions. Here, this alternatives, I am calling it as solutions. We can try different solutions. We will obtain the objective function and we'll say, okay, this seems better. We can go with this. That doesn't mean that this is the optimal solution. This is the best we can do. It just says whatever we have seen so far, it is the best we have seen yet. Okay. Applications of Chinese Postman problem. Again, this is not a toy problem. It is applicable, widely applicable. Robotics and path planning. So for example, if you see now that there are many robots, cleaning robots. So those robots optimize the path they cover. So they'll see some obstacle, they can turn again and so on and so forth. In those cases also, he is traveling across some path and they can try to minimize the distance they are traveling to clean the whole surface. Okay. Transportation and logistics. So for example, a milk delivery milk delivery van. They are also doing the same thing. They has to deliver the milk in all the houses or maybe some of the houses in the lanes. And what they will do, they will try to minimize the fuel consumption or maybe the time taken to perform the deliveries, satisfying the constraints that they cannot jump from one node to the other and so on and so forth. Urban planning. It aids in garbage collection. So the garbage truck has to travel all the lanes in a city and they have to collect the garbage from each of the houses. So this is very similar to the Chinese Postman problem. street cleaning, or maybe in cold countries there is something known as snow removal machines where they have to remove snow from each of the lanes. So over there also this Chinese postman problem applies. So you have to remove snow from the lane, and obviously you have to do it for all the lanes, and you just cannot jump from one point to the other. Game development, optimize the path of a AI controlled agent in a gameplay. Inventory management, so if you have a warehouse where you have kept some of the stocks in the warehouse and you have to do something in the warehouse, so or maybe clean something there in the warehouse, or maybe efficient inventory access or something like that, in those cases also these problems are applicable. So I'm not giving you exact applications, but some form of this problem may be applied to those areas.
How to solve the Chinese postman problem?
So we will talk about solution methods in this workshop. We are just seeing what this problem is and understanding the ways we can approach this problem. We will see some ways of solving this problem. I will not be able to tell you all possible solution approaches to that problem, but yes, at the end of this workshop, you'll know how to solve that problem. All right. Okay, so drone and aerial surveillance. So this can also be seen as an application of Chinese postman problem. Okay, so before we proceed further, we have completed 1 hour. We can take 5 minutes break and we'll meet at 6:36. Okay. If you have any doubt, you can write it in the WhatsApp group. I will be available at 6:36. Okay. Thank you.
So if you have any doubt, you can write in the WhatsApp group uh, regarding these sessions.
So I hope you are back. So before moving forward, we will have a brief introduction of the decision-making process. So this is not the exhaustive list or maybe steps of the decision-making process, but these are broad categories on how on decision-making process. Okay. So first of all, we have to identify the problem. And this is, I have named it as formulate. So we identify the problem, the objective function, and various factors influencing that problem. So in any industry, if you face a problem, you might not know exactly what constraints are there in the problem. You may know that, okay, I want to decrease the production cost of my product X. This you will know because these are direct, these have direct implications. So that is the objective function, but you may not be able to know what are the constraints immediately. You'll have to sit down, study the problem again and again, and then you will realize what are the constraints in the problem, what are the governing variables in that problem, not variables, parameters of that problem, and so on and so forth. So you have to identify your problem, the objective function, the constraints, and other factors that influence that problem. Once you have done so, once you have identified that problem, then you can proceed to model that problem. While modeling that problem, you have to remove unnecessary details from that problem. So the way we did for that bridge problem, right? A simplified mathematical model, it may be inspired from existing, why have I written solution inspired from? So I have to check why I have written solutions, but yeah, it can be inspired from an existing model, or you can make a new mathematical model on your own, right? And generally we make a lot of simplifying assumptions because solving a simplified model is easy as compared to solving a very complex real world problem. Okay, so we make some simplifying assumptions and then we model the problem. We use so this means we approximate some of the parameters, we make assumptions such that we focus on the core aspect of that problem. Then we optimize. So I have not defined what optimize is. It is in the next slide. For the time being, just assume solving the model to obtain a good solution. Okay, again, these optimal solution, suboptimal solution, just for the time being, ignore. To obtain a good solution. Once you have obtained a solution to the problem, you go back and give it to the manager. So there are two identities, not identities. There are two persons involved here. This is an optimizer. You can call him an optimizer or a person who solves the problem. These two are decision makers. Okay, decision makers. So the task of the optimizer is to get the details from the decision maker, model that problem and solve that problem. Once you have solved that problem, you give the solution to the decision maker. He will tell you whether that solution is feasible, possible or not. So what may happen is when you have simplified the problem, you may have simplified it to that extent that the solution which you have obtained is no more applicable to real life. So this decision maker will then come back to you and say, boss, the solution which you have provided is not appropriate. Please check your model again and then give me a solution. Or maybe he can come back and tell you, okay, the solution which you have obtained is, it looks good. We can go ahead with that. Okay, so that is what it means by iterate and implement. Refine the model and algorithm to improve the solution. So just a minute. So from time to time, you may either have to refine your model or maybe you have to define your solution approach. Okay, either of the two, you have to check when you obtain more details from the decision maker. So if you see that your model is not appropriate, you may have to ask the decision maker for more details. But if you see that your model is appropriate, but the solutions obtained from your model is not good enough for the decision maker, then you may have to improve your solution approach. Okay, so either of the two can work. So there were some hands I saw, so you can just unmute and ask me.
I had one quick question. Like in some point previously in the discussion, we said like once the problem is formulated, we need to check if it is actually solvable.
Right.
So would that come under the second point? Like before you build the model, you do that, or where exactly does that step fit in the decision-making process?
So first, coming to that question, I'll like to point out whether a problem is solvable or not is a very, I'll not say difficult thing, but it's a very technical thing. Solvability of a problem is very not subjective, but it requires more details, more knowledge of defining that a problem is not solvable. There is a whole field of there's an area known as complexity theory, which deals with whether a problem is solvable or not. What do you mean by solvable? It is again a big thing. The second part is where does it fit here? So when you build a model, that doesn't require you to think about how you will solve the model. When you are building the model, you just have to see whether the problem which you have obtained from the decision maker and the model which you have made, does it represent the problem or not? So again, I'll repeat, the model which you have built should represent the basic problem which the decision maker brought to you. If that is the case, then point number 2 is done. When you're trying to solve that problem, then comes the question whether you will be able to solve this model or not. If you will not be able to solve this problem or not problem, if you will not be able to solve this model, you go back to the model, build another model, and then try to solve that problem. So it may happen that a problem which you have formulated in formulation A is very difficult to solve. But the same problem, if you formulate it using some different variables and you get a formulation B, then it becomes easy to solve. So the same problem in two different formulations can be difficult to solve and easy to solve. Again, difficult to solve, what does it mean? Easy to solve, what does it mean? It requires more depth. So I will just restrict myself to just difficult to solve and easy to solve.
Thank you.
Okay, any more questions? Okay, so this is just a brief yeah. Yes, Ajay. You are not unmute. You can unmute yourself and then speak.
Just, yeah. Is it similar to the simulation or is it design thinking process?
Sorry?
Is it similar to, is a simulation people are doing or is a kind of design thinking people are creating to solve any problem?
So what I will tell you is when we are trying to model and optimize, you can either go either way. You can use simulation to solve that problem, or you can use methods.
Where if you see during the simulation, we will just try to see what are the different variable and we will try to put and then we will see what kind of output people are getting.
Yes. Actually, I have not experienced with simulation work. So I guess Professor Sandipan is
actually, in case of simulation, what we used to do, we used to vary the parameter. We used to take the decision by ourselves whether the output is optimized or not. Whereas this is the mathematical problem will be solved using some numerical equations, which if we solve will give us the optimal solution. So yes, simulation based optimization also is there, but in that case commonly either we have to take the decision or simulation if gives the output and there is another optimizer which if we connect together, then that optimizer will take the decision automatically and move to the next point at which your circuit or your model or your the entire model will be simulated. Through that iteration, it can reach to the optimal solution.
Yeah,
So
thank you very much.
Yeah. I think, is it clear or some doubt?
Yeah, I think thank you very much for your insight. I'm basically automobile engineer. I was just thinking how to correlate, because in the automobile industry, lot of simulation people are doing. Like if you see how to enhance the
Yeah.
efficiency of the car, what is the weight of the car, what are the even the width of the tires. All these are the different variable, and the based upon that we used to do some simulation, so that what is a kind of
Yes.
optimal method and what are the different constraints, so that people are able to get the best kind of output, and even the power, even the efficiency, and all these things.
So I found
Exactly. What you said is perfect. Means probably you are using, say, ANSYS. So if the ANSYS is having, I am from electronics background, so I have not used ANSYS. But if ANSYS is having the optimization tool, then ANSYS can reach to the final design even. Or if ANSYS you are using to design using ANSYS, and output you are taking in the MATLAB, and MATLAB optimizer or any optimizer, maybe Python based optimizer, if that optimize and move to the next iterative way, so there this handshaking will help is to reach to the optimal solution.
Sir, I would like
Yeah,
I would
sorry,
like
but
to
I will, like, one question there. It is similar to the, is it design of experiment where a lot of variables and the different outcome we people are expecting, and then we just do some changes in the variable and see what kind of output people are getting.
Yeah, you will
Yeah,
be observing
we
at the,
use
yes.
Minitab in our system, and where we people are doing lot of simulation based upon the input parameters and what are the different constraints related to the individual parameters. I am really sorry. I think, sir, please continue. Yeah.
yes. So just one thing I would like to add. So when you were saying automobile engineering, then I got some idea. So what is happening is in automobile, you are trying to obtain that objective function. You will plug in some values of the variables and you will see what is the objective function. Over there, you don't have a closed form equation of the objective function. So using the simulation, you are trying to obtain at these values, what is the value of my objective function? Maybe I'm not correct, but this idea I am getting. Okay. So there is one
Thank
more
you.
hand. So yeah.
Yes, sir. Actually, in industrial engineering, what happens? The person has said about the student has said about the automobile engineering thing. So one of our industrial engineering students actually worked upon the gear design, and he has designed in the ANSYS. So he has applied the design of experiments, that is the Taguchi's method, for optimization, and then accordingly he has put the thing into the ANSYS model for modeling the gear. So that is optimized result actually. ANSYS do not give the optimized output actually, but you can apply the optimization tool in order to optimize the parameters and then apply it for designing in the ANSYS.
Okay. So I am proceeding, right?
Yeah.
Thank you for so much for the clarifications.
Hmm.
Okay. So yeah. So we will proceed. So what is optimization? Optimization is a process of finding best solution from a set of possible solution based on defined criteria. So this is not a technical definition of optimization. It just says we are trying to, it is a process of finding the best solution from a set of possible solutions, right? There can be multiple solutions satisfying the constraint. We are trying to get that best solution based on a defined criteria. Technically, optimization is a process of finding a solution to a problem that satisfies the constraints. Again, I have not defined what constraint is, in order to maximize or minimize the objective function. Okay. So what is the objective? We are trying to get best performance under a given criteria. So this is the idea of optimization. More technically, in mathematically, you can write an optimization problem as a pair S, F, where S is a set which is the search space. So it contains all the points, all the feasible solutions. S is the set of the feasible solutions and it is known as search space. So suppose if you have two variables x, y, so x can be the set of all possible x, y, all possible x, y. Okay. So that is known as search space. Whatever the value of your decision variables are, the set of all possible values which are feasible is known as search space. What is f? F is the value of the objective function, right? So at a given s, small s, at a given s, suppose 3, 4, you will have a value of f. So if you go back to the example of that pen and notebook, for some 10 pens and 5 notebooks, you had a value of your objective function. So for each s, you have a value of f. So f is the objective function, a metric that evaluates, and we have to maximize or minimize. So an optimization problem can be formalized as a pair s comma f, okay, where s is the search space and f is the objectives function. And if it is more than one dimension, over here we are saying that it is single dimension, that is why I'm saying objective function, but it is more than one dimension. What do I mean by more than one dimension? You can have a problem where you are trying to minimize two objectives. For example, in a production line, you are trying to minimize the cost of production as well as you are trying to minimize the time it takes to do a process. So there are two objective functions. In that case, it becomes a tuple. You are trying to minimize both objective function. So more technically, you can say you are trying to you have optimization problem, a search space and an objective space. There are two kinds of spaces in your problem, a search space and an objective space. What is the goal? You're trying to find the global optimal solution. What is that solution? We are representing is at s star and f of s star. So the value of the objective function as at s star is always less than equals to f of s, where s is all possible solutions in the search space. So this solution we are trying to find, that s star which is least among all possible solutions in the search space, and this is the definition for a minimization problem. Okay, so this is how we obtain an optimized solution, global optimal solution. This is what an objective function is. This is what an search space is. These are technical definitions of this. So optimization plays a crucial role in the field of resource allocation, decision making, machine learning, engineering, finance, logistics, and many more. I have given real life examples. We have been seeing more examples. So I have just listed few down. A logistic company use optimization to minimize delivery time by selecting the best route for its fleet. So what he is doing, he is trying to get that company is trying to get the best route to deliver items. Okay, so this can be thought of as the Chinese Postman problem. If you think that the nodes are the corners in the city, and for each lane you are trying to deliver some item in the houses in that lane, then it is a Chinese Postman problem, right? But it can be thought of as a different problem also. I will discuss that problem in a little later. Okay, the Chinese Postman problem focuses on the lanes, the edges. Edges has to be traveled exactly once. In edges, not exactly once. In the edges has to be traveled, must be traveled. All edges must be traveled, right? And the objective is to minimize the delivery cost, meeting the customer deadline. Okay. So search space and objective space, the set of all possible solutions for an optimization problem. Example, so we have not discussed a traveling salesman problem. For example, Chinese Postman problem. The search space consists of all possible routes. Okay, Chinese Postman problem. So the search space can consist of all possible routes. Objective space, the space defined by the value of the objective functions for all possible solution. Each point in the objective space corresponds to an evaluation at the point in the search space. So each point over in the search space will evaluate to, have I written it? I guess each point in the objective space corresponds to the evaluation of a point in the search space. Yeah, it is written appropriately. So each point in the search space will evaluate to a value in the objective space. So you have a search space. It is a two-dimensional search space x comma y, and this is a two-dimensional objective space f1 comma f2. Okay, so in this direction you are specifying what is the cost, and in this direction you are trying to specify what is the time. So it is a two-dimensional objective space and a two-dimensional search space. Okay, so this is the relationship between search space and objective space. What are we trying to do? We are trying to find that solution S star which minimizes. So suppose it is a single objective space where there is only one objective function. You're trying to minimize that objective function, and you're trying to find that solution in the search space which minimizes the objective function for a single dimensional objective space. Okay, and again in this whole workshop we will only deal with single dimensional objective space, so we'll have only one objective function. Okay, for the whole discussion in this workshop we'll not go to multi-objective problems, we'll only focus on single objective problems. Just for the sake of illustration I have shown you two-dimensional, but we will only focus in single dimension. Now we'll go to the first method of solving an optimization problem, that is known as brute force method. Before proceeding, any questions? Okay, so what is brute force method? Brute force method is an exhaustive approach that evaluates all possible solutions to find an optimal one. So what we'll do in the search space, we will find all possible solutions that satisfies the constraint, all possible feasible solutions, and we will evaluate each of the solutions, and then we will pick the best one. How does brute force search work? Brute force work, enumerate all possible solutions in the search space, evaluate each solution using the objective function, select the best solution Okay. For this brute force method, to show the limitation of brute force method, I have taken an example problem which is known as the traveling salesman problem. And please be mindful, I will discuss this problem and it is a very, very important problem, widely applicable, and we'll use this problem in tomorrow and maybe the next class, next 3 sessions as well. So this example problem will be used to discuss the various algorithms. Okay, so please be mindful. So what is a traveling salesman problem? A traveling salesman problem is different from a Chinese postman problem. We will discuss the difference after we have discussed what a TSP is, traveling salesman problem is. So in a traveling salesman problem, you have a graph. So there are some nodes and there are edges between these nodes. Okay. There are nodes and there are edges between these nodes. The problem is to visit each of the nodes. So when cities, I say, I have represented cities as nodes. The cities are nodes and the edges, so I'll write nodes are cities and the edges are roads or paths. Sorry. Okay. So that this traveling salesman problem, what does it mean? It says that there is a salesman who wants to visit each of the city exactly once. Each of the city exactly once and come back to its origin city. So he will start from the origin city, suppose city A, and he has to visit each of the city. It doesn't matter which route he takes. He can take any route. He can visit any city in the order. He can go from A to C, A to D, A to X. It doesn't matter. But he has to visit all the cities. So if there are A to Z cities, 26 cities, he has to visit all the 26 cities. There's a base city. So for the time being, I'm saying A is the base city. So starting from A, he has to visit all the cities and come back to A. The edge doesn't, so we are not focusing on the edge. In the Chinese postman problem, we were focusing on the edge. He has to, so in the Chinese postman problem, he has to visit each edge. But over here, he has to visit each node. He has to visit each city. So that salesman has to visit each city exactly once, starting from one node and come back to that node. And the objective is to minimize the total distance he is traveling, or maybe the cost he is incurring to travel the cities. Okay. So if you see this diagram, and if A is the starting node, you can say that A to B, B to C, C to D, D to E, and E to F is one route. That is one solution to this problem. You can have different solution to this problem. So what is the first solution? A to B, B to C, C to D, D to E, and back to A. So this is one solution to this problem. Another solution we can have A to D, and D to E, and then okay, D to E, E to C, C to B, and B to A. This is one more solution to this problem, right? So there can be multiple solutions to this problem. You are trying to find the best route this traveling salesman can take. Okay. Is the difference clear? The difference between traveling salesman problem and the Chinese postman problem? over here there is no restriction that you have to visit all, you have to take all the edges. You can leave out some of the edges, doesn't matter, but you have to take the route such that you visit each of the nodes. In Chinese Postman problem, the problem was you have to visit all the edges, right? So these are different problems. Application, some application you can think of like these are, so you can think about as a delivery, Amazon delivery. So there is a person who is delivering parcels and these nodes represent houses. So house A, house B, house C, house D, house E. He has to go to each of the house and come back to the center where he is taking the parcels. And then he has to find out the route which minimizes his time, because he thinks that his time is more important, or maybe he wants to minimize the distance he is traveling because that will minimize the fuel cost, and so on and so forth. So those are applications of traveling salesman problem. Okay. Applications of, oh, I have written applications of Chinese Postman problem. So logistics and transportation, routing of trucks for efficient delivery, routing of flights for airline to minimize fuel and time. So you can think about as airports as nodes, and then that flight has to visit each of the nodes, right? Routing of flights, car navigation system for finding the shortest travel route. So if you go to the Google Maps and if you find the route from city A to, suppose, place A to place B, it is solving some kind of traveling salesman problem. He will see some kind of, it's not exactly traveling salesman problem because he's trying to solve the shortest route problem. Starting from A, you have to go to B. So what is the best route it can take? It is not exactly traveling salesman problem, but very similar problem in nature. Manufacturing of and warehousing, order picking. So I have told you about Amazon delivery. It is that warehousing and manufacturing. Circuit board drilling. So there is a circuit board and there are some holes where PCBs or some other transistors. I am not from electronics, so please apologize if I use some wrong terms. So there are some holes that need to be drilled on that circuit board, and there is a drill which goes from one hole to the other, drilling at each point. Now, if you think about just one circuit board, it doesn't matter if you go from one path or the other because it will take fraction of a second to, not fraction of a second, fraction of a minute to drill all the holes. But think about this at a production factory, mass production factory. The time spent, the excess time spent for each drilling compounds. So for each of that, you have to incur more time. So efficient drilling path is important. What is the efficient drilling path? That the time to drill the circuit board is minimized, and that reduces a cost a lot. Okay. Agricultural routing and so on and so forth. There are many applications. You can go in the net and you can search many more applications of traveling salesman problem. Okay. Now we were talking about brute force method. Why did we come to traveling salesman problem? That we will explain using this slide. You see, the traveling salesman problem is faces a major challenge due to the huge number of possible routes. So suppose there is a graph where there are 7 nodes. So you see, you are starting with the base nodes, node A, so that is fixed. Now you can create 6 permutation of the different cities that can be filled. So A, B, C, D, E, F, and so on and so forth. So 1, 2, 3, 4, 5, F, G, right? So there are 6 factorial permutations that can be built, right? For a problem of size 7. But there is symmetry also. So A, B, C, D, E, F, G is same as G, F, E, D, B. G, F, E, D, C, B, A. So this and this is exactly the same because there is symmetry. If you go from A to B to C and back to A, and A to C to B and back to A, those 2 routes are the same. So it becomes 7 minus 1 factorial by 2. These are the number of possible routes that problem has, number of feasible solution that problem has. So if you are trying to solve using brute force, these many solutions you have to check. What is brute force? For each of the solution, you find the objective function and pick the best. So if you have a city, if you have 7 city problem, you have to solve 7 minus 1 factorial, that is 6 factorial by 2 number of solutions. And for each of the solution, you have to obtain the objective function and then pick the best. Okay, so this is the number of possible solutions in a traveling salesman problem. This is the search space of that problem. Number of problems in the search, number of solutions in the search space. Okay. Before proceeding, is it clear or am I going fast? Because I have a tendency to go fast. Okay. Okay. So these are the many number of possible solutions for a traveling salesman problem, where n is the number of city. So n minus 1 factorial by 2. So why brute force is unfeasible? So we are assuming that a computer can compute one solution per microsecond, 10 to the power minus 6. This is the time a computer can take to compute a solution. What do I mean by compute a solution? So given a solution, it can obtain the objective function. So in 10 to the power minus 6 seconds, a computer can obtain the objective function. Okay, so that is the time it takes to solve that objective function of a solution. So for a 10 city problem, this brute force method will take 0.18 seconds. For 11 city problem, it will take 1.81 seconds. For 12 city problem, around 20 seconds. For 15 city problem, 12 hours. For 20 city problem, it scales up to 1928 years. So if you have got a real problem where there are hundreds of cities and you are trying to solve that problem using brute force method, the whole universe will end and you'll not be able to solve that problem using brute force method. You just go from 20 to 21 and you see this number, how large it gets. It will jump exponentially. Okay. So what is the conclusion? Even for a small value of n, brute force search become impractical. Therefore, there is a need to find better solution approach. Okay. Any doubt? Okay, so limitation of brute force: computationally very expensive, impractical for large problems, and I have used this term time complexity, and we have not discussed this a lot, so I'll just skip this point. If you are interested, you can take up it in your leisure time and read about time complexity. Key takeaway: the brute force method guarantees an optimal solution, but it is computationally infeasible for large problems. What do I mean by guarantee an optimal solution? You see, if you perform brute force method, it is guaranteed to give you an optimal solution. Unlike metaheuristics, we have not talked about metaheuristics, but unlike metaheuristics, where there is no guarantee of optimality, this solution method guarantees optimality. So if you follow this method, you will be guaranteed to get an optimal solution, but it doesn't matter because it is not practically feasible to perform brute force method. Okay. So we'll proceed to classifications of optimization method. This chart I have taken from this book, the book which I have referenced earlier. So it's the same book. So optimization methods can be classified into two broad groups: exact methods and approximate methods. Mind you, it is approximate method. So exact methods can again be broken down into these classes. I will tell the classes, but we will not go on to exact methods. This workshop is focused on a particular category, which is just this part. Okay. So having said that, let's see what are exact methods. Branch and X. So this X can be many things: branch and bound, branch and cut, branch and price. Constraint programming, dynamic programming, A star, and there are more methods on exact methods, right? Approximate methods. Approximate methods had two categories: heuristic algorithms and approximation algorithms. You see, this is approximate and this is approximation. Okay, so approximate methods had two classifications: a heuristic algorithm or an approximation algorithm. We will not talk about this as well. Heuristic algorithms can be broken down into two different categories: metaheuristics and problem specific heuristics. We will talk about problem specific heuristics today, and this workshop is about metaheuristics. So broadly classifying metaheuristics under single solution based metaheuristics and population based metaheuristics. Okay. So I am running out of time. I have a lot of things to discuss. I'll try to complete in some time. Okay. So exact methods obtain global solution and guarantee optimality. So examples, I had shown you some examples over here: dynamic programming, branch and bound, branch and cut, branch and price, constraint programming, A star, and so on and so forth. We will not talk about exact methods in this workshop. Approximate methods. Approximate methods provide good quality solution within reasonable time. Categories, heuristic methods and approximation methods. So if you come over here, approximate methods are divided into two categories, heuristic methods and approximation methods. I'll just give you a hint what an approximation method is. It also gives you a suboptimal solution. I'll not say suboptimal, it gives you a solution where you don't know whether it is an optimal or not. Okay, it gives you a solution where you don't know whether it is optimal or not, but you know the quality. You will be able to say, okay, this is this much better. Okay, so this is an idea of approximation methods. In heuristic, you know that it is not, it may not be optimal. You also don't know the quality. It may be very bad, but you don't know whether it is bad or not. In approximation, there is some bound कि हाँ इससे खराब नहीं हो सकता. This is the worst it can get. But in heuristic, you actually don't have an idea how bad the solution is. But nevertheless, it has some advantages and we are using it. We are here for a workshop of it. So yeah, it is practically applicable in many fields. Okay. Focus on good quality solution quickly. Lack approximation guarantee. Okay. So over here I have written heuristic algorithms and I have written lack approximation guarantee. This is not correct because approximation comes under. Just a minute. Okay, I'm sorry, I was confusing you. I'll start again. So heuristic algorithms focus on good quality solutions and it gives quick solutions. It lacks approximation guarantee. That means it will not be able to say how bad is the solution. Okay. It includes problem specific heuristics and metaheuristics. Approximation methods, it offers some bound on the quality of solution and runtime. So it will be able to say कि हाँ this solution is this much, it can be this much bad, इससे bad नहीं हो सकता. Okay. Examples, I'll not go into this. Applicability, best suited for large and complex problem instances where exact methods are not feasible. So there is a class of problems known as NP hard problems. That term has come from complexity theory of problems, which says that some problems are very difficult to solve in large scale. And in those cases, exact method fails. And hence we use approximate methods to solve such kind of problems. Okay. So exact versus approximate methods guarantee global optimality. And so I'll see guaranteed global optimality. It gives approximate methods give near optimal solutions. Computational cost for large difficult problems. Exact methods have high computational cost. Approximate methods have low to moderate computational cost. Scalability, what do I mean by scalability? It means if the problem size increases, how well your approach works. That means for a traveling salesman problem, you have a problem of size 10, you have a problem of size 100. So you have scaled the size of the problem, how well your solution approach is. So exact method is poorly scalable. It doesn't scale well. So for large problems, it performs very badly. But approximate methods had good scalability. Examples. So we have seen some examples. Okay. Problem specific heuristic. When I say problem specific heuristic, we are talking about, so we are here. So we are here. So we have talked about approximate and exact methods. We will not go into approximation methods. Just a minute. We have seen heuristic. We will classify the heuristic into metaheuristics and problem specific heuristics. So we are here. We will talk about problem specific heuristics now. Yes, Siddharth.
Sir, I'm little bit confused about heuristics and approximation. Can you differentiate it?
Yes.
Because somewhere in the approximation algorithm, you have given example of heuristic item.
No. So this is important. You see, this is approximate method. Approximate yes. Method. And over here, we are saying approximation algorithm. Okay. Yes. So approximate methods had two class. So if you come over here, approximate methods had two categories, can be divided into two categories, heuristic algorithms and approximation algorithms. Approximate method ka kya matlab? It means that your solution is not guaranteed to be optimal. It may be optimal, it may not be optimal. Okay, that is what is meant by approximate method. So it has two kinds of algorithms. One are approximation algorithms. So it says that approximation algorithms, when used, it will give you a solution where it might not be optimal. It may be optimal, you don't know, but it is guaranteed a bound कि इससे खराब नहीं हो सकता. There is this bound, at this bound इससे खराब नहीं हो सकता. That is what it means. But heuristic algorithm doesn't have a bound. It doesn't specify anything about a bound. Okay.
It may be worst also.
Generally it is seen it produces good solution. But yeah, for some very complex problem, those solutions may be very, very bad.
Thank you.
Okay. Problem-specific heuristics. So problem-specific heuristics are designed to find good solutions quickly, often based on domain knowledge or intuition. Okay, so this is problem-specific. Advantage, it is simple and computationally efficient, effective for small and well-defined problems. Example, greedy algorithms, rule-based algorithms. So we will see greedy algorithms for knapsack problem. We have not discussed knapsack problem, and we'll see greedy algorithms for traveling salesman problem. Limitations, it doesn't guarantee to find optimal solution. We have talked about this. Can perform very poorly for complex and poorly understood problems. Okay. Okay. So before moving on to problem specific heuristics, let us introduce what a meta-heuristic is. We are at a workshop of meta-heuristics. This definition is appropriate over here. So a meta-heuristics is a family of approximate optimization techniques that have gained popularity due to its flexibility and effectiveness. What are the key characteristics? It provides acceptable. So you see these are in quotes. It is not technically appropriate to write acceptable. That's why they are in quotes. It provides, why it is not appropriate? You see, for some it may be acceptable, for some it may not be acceptable. So the definition of acceptable varies depending upon the application. That's why it is in quotes. It provides acceptable solutions within a reasonable time frame, ideal for solving complex and real world problems in science and engineering. Do not guarantee optimal solution, but focus on finding good solution efficiently. Highly flexible and adaptive across different problem domains, widely used in various fields, including logistics, scheduling, machine learning, engineering design, and so on and so forth. Why meta-heuristics? They are practically useful when exact optimization methods are computationally impractical due to large search space and complex constraints. I hope you are getting the idea of why exact methods are practically impractical. So I have given you the example of brute force search, right? Where it becomes infeasible to solve such kind of problems, impractical to solve such kind of problems using exact methods. Okay. Now we'll move back to problem-specific heuristics versus meta-heuristics. Comparison of problem-specific heuristics with meta-heuristics. You see, heuristics has been classified into two categories: meta-heuristics and problem-specific heuristics. So what are we trying to do? We are trying to see what is the difference between problem-specific heuristics and meta-heuristics. Okay. So problem-specific heuristics are simple and faster. So it is because it is using some property of that problem to solve that problem, right? But meta-heuristics can be slow because it is a general purpose solving tool. It is a general purpose framework for solving wide range of optimization problems. So simple terms, meta-heuristics are a general purpose algorithms. It can be applied to many diverse problems, and problem-specific heuristics uses some feature of that problem to find good solution. It may not be applicable to some variation of that problem. It is just applied to that problem. Okay, so that is the idea of problem-specific heuristic and meta-heuristics. Now this is a very important question: when to use meta-heuristic? So it may not be wise to always use meta-heuristics. There are some specific indications when you should use meta-heuristics. So meta-heuristics are useful when exact methods are impractical due to complexity and time constraints. So again, I have not defined what NP-hard problem is. For the time being, assume that those are problems which are very difficult to solve. It is not a technical term, not technical definition. So meta-heuristics are applicable, or we should use meta-heuristics when the problem is NP-hard and large size. Okay, exact methods are too slow for large and real-time instances. Instance is complex, so it may happen that your problem can be solved using an exact method, but that instance, matlab, so you see, traveling salesman problem is a class of problem. You can have 5 cities, 10 cities, 30 cities, 50 cities. So when I say 30 cities, it is an instance of traveling salesman problem. Okay. So traveling salesman problem is a class of problem which I'm calling problem. And an instance of that problem means one example or one instance of that problem, 30 city problem. Okay. So some instance can be very complex and prevents optimal solutions. Okay, so in those cases where that instance is difficult but the problem is not, but that instance is difficult, then you can use meta heuristics. No efficient polynomial time algorithm exists. These are all technical terms. If you are interested, you can contact me later, we can discuss about this later. Okay, avoid meta heuristics when efficient algorithm exist. So for shortest path problem there are efficient algorithms. So we have not talked about minimum spanning tree problem. For the time being, we can ignore now. The size of the problem is small and can be solved optimally. So suppose you are having a traveling salesman problem, which is an NP hard problem, but you are solving a 7 city problem. So you can use exact methods because it is a 7 city problem that can be solved using exact methods. You shouldn't use meta heuristic for a 7 city problem or 10 city problem, right? So you should avoid meta heuristics in such cases. You should avoid meta heuristics or approximation methods where it is unnecessary. So some problems may not require you to use approximate methods. Like for example, there is a classification of design problems and planning problems. Sorry, design problems and operational problems. So I'll explain what design problem and operational problem is. Design problem is a problem when you're trying to build something. So for example, you're trying to build a city and it requires a lot of investment and it cannot be changed. So it is a one-time decision. So that is known as a design problem. For those problems, you have a lot of time in your hand because if you get a suboptimal solution and you implement that, then it will cost you, it will have recurring effect. So that problem is very important to you. It is a design problem. In such cases, we try to obtain good solutions because you have time, you have money to dedicate on those kind of problems. So generally in those problems, we don't use meta heuristics. Generally, it may happen that you use. Nevertheless, general idea is you don't use meta heuristics in design problems. Operational problems are problems which you, for example, every day there is a person who is doing delivery of Amazon delivery. That is an operational problem. It is faced every day. So you don't have time to spend to solve that problem. So in those cases where time is important, you have to do it quickly. For example, train disruption. So there is some delay in train and you cannot wait for 10 hours to solve that problem using exact methods. You need quick solutions. In that case, we use meta heuristics to solve that problem. Okay, so design problem and operational problems. Conclusion: meta heuristics are best for large complex and hard to solve problems where exact method fails. Okay, so for the sake of completing in time, I will skip linear programming for now, but I'll give you an idea. So linear programming is a mathematical optimization technique where the objective function, the constraints are all linear and the variables. So linear means it doesn't have higher orders or log or some other functions. Those are linear. And the variables take real value in a range. Yes, sir.
As we started little late, 10-15 minutes late, so today we can reach up to 7:45 also.
Okay, sir. Thank you.
So 10-15 minutes more is okay.
Okay, sir. Okay. So I hope for the participants also it's all right.
Yeah,
okay.
I think that is okay. Or one thing we can do at 7:30, we can share that the way we plan for the attendance.
Yes, sir.
After that, if somebody is having, because already we planned to complete it by 7:30. So if somebody is having other engagement, he or she can leave. Okay. And but you can take 10-15 minutes more. Instead of going hurry, you can take your little more time. That is my opinion.
Right, sir, I'll do. So for linear programming problems, these are mathematical optimization techniques used to find best possible solution. So these are optimization problems. So we are trying to find the best possible solution, which involves linear objective function. So that objective function is linear. The constraints are linear. And I guess I have not written here. I should have written the decision variable, that is X, Y, Z, something like that. Those are real valued. Okay. So suppose from 2 to 5 or 0 to 10 or something like that, it should be real valued. Okay. So these are linear programming problems. I have given one example. It will be clear from that example. So that budget problem. So instead of discussing this problem where you can go back and see this problem. Okay, budget problem. No, let us move on with this problem. A factory produces two products, product A and product B. The goal is to maximize profit while considering production constraints. So product A, so suppose oil 1 and oil 2. So it produces two oils. So oil 1 has a profit of 5 rupees and oil 2 has a profit of 4 rupees. So there are some constraints on machine hour constraint. Each unit of product 1 requires 6 hours and each unit of product 2 requires 4 hours. So what is the time taken for product 1? Product 1 takes 6x hours. So if you are producing x quantity of product 1 and per unit product 1 takes 6 hours, the time for product 1 produced in x quantity is 6x, and product 2 it will be 4y. Okay, so I am representing the quantity of product 1 as x and quantity of product 2 as y. So 6x plus 4y is the total hour spent to produce x quantity of product 1 and y quantity of product 2. And the factory has a total 24-hour availability. So this should be less than equals to 24. Okay, and you see these oils can be produced in real values, right? 0.5 liters, 0.05 liters, and so on and so forth. So these x and y are real numbers, and we'll say x greater than 0 and y greater than equals to 0. Why? Because you cannot produce negative quantities, and it can take real values as well. Okay. Another constraint is the labor hour constraint. Each unit of product 1 requires 1 hour, so 1 times x, and each unit of product 2 requires 2 hours, 2 times y. The factory has a total of 6 hours available, so it is less than equals to 6. So these are the two constraints it has. This is the two constraints, and these are the two non-negativity constraints. Okay.
Shubham, just a minute. Can we just pause for 4-5 minutes to complete that attendance?
Yes.
Because one participant is from Malaysia, and yes, she might be getting late. So
okay.
let us stop here for 4-5 minutes, and again we shall start. Okay, that will be better, I think. Okay, so just wait. The link I'm opening. And so you can also open the link at my end. I don't know.
I will share the link, sir.
No, link I have shared, but okay. Only that it has to consider to accept the attendance.
So you have shared the link, right?
Yeah, I have shared the link.
Okay. So it is accepting, sir.
I don't know what happened to my.
Sorry, I'll just check, sir, once more.
No, still it is not accepting any input. It is not opening.
Just 1 minute. I'll just.
Just a minute. It will be done.
Yes. Sure.
Yeah. Now I think it is. Now it is accepting. You just check. Now it is accepting.
Yes.
Yeah.
Now it is accepting.
So please write this code
in that link, the code will be asked. Please write this code MTH2562.
MTH2562.
Capital MTH2562. This is only to ensure that whoever are attending with full attention can give the.
And what about the students' attendance code? That is also same.
Sorry.
Which one?
Acha, one thing is that registration ID. Acha, okay.
Registration ID has been sent through mail.
Okay. Got it.
Yeah, thank you. Today's attendance code is this code, MTH2562. At the end, there is a your view and what suggestion or any other comments. Request, please. That part is not mandatory, but we request, please, you give your feedback so that next 3 days can be more effective.
So what is the registration ID?
Registration ID has been sent through mail. That mail is having one.
You can find it in that PDF. In
PDF.
that PDF.
That
meta underscore something. Meta underscore something.
Yes.
40.
I will share that PDF in the WhatsApp group once. So
yeah, I am sharing. This PDF I have shared, you can check your registration ID, except only today whoever has joined. Yes, there is a hand raised. So if you want to share something,
you can unmute yourself.
This is a quick question regarding the lecture. So you had mentioned that we would not use, or it is not advised to use metaheuristics for a small problem. Is it only because that approach would be an overkill, or also because it might, and you might end up getting a very bad solution despite using metaheuristics?
Ma'am, there is a better answer to this question. So if you use a meta heuristic for a small problem, you may get an optimal solution. And I guess in most of the cases, you'll get an optimal solution. But the problem is you will not be able to say anything about the quality of the solution. You will not be able to say that this is an optimal solution. It is a very strong conclusion. If your solution is optimal, you have come up to a very strong conclusion that for this problem, there is no other solution better than this solution. If you use an exact method, but if you use a heuristic or a meta heuristic, you may have an optimal solution, but you'll not be able to say. So suppose you're writing a paper, and in that paper you have used a meta heuristic, you will not be able to say कि इससे better नहीं हो सकता. It is, but if you use a exact method, you will be able to say कि this is the optimal solution I have obtained. Nobody can do better than this for the instance I have. Yes, ma'am, you can speak. You are mute, actually. I'm not able to hear you.
No, I understand when you have an exact method that it is always good to go for that. But then when you don't have an exact method, then
So again, when I was discussing the slide where we were talking about when to use meta-heuristics, there are other aspects to consider as well.
Just Shubham, just a minute. Please don't share this code in WhatsApp group. Please don't share this code in WhatsApp group. Just now I deleted once. Okay, thank you. Yeah, please proceed.
So I was saying, sir, ma'am, when you suppose you have a very non-linear problem, very small instance non-linear problem, and you don't have an exact method to solve that problem. In such cases, you may use meta-heuristics. So when I said don't use a meta-heuristic for small size problem, I also implied that that problem is simple to solve. Professor Sandeepan, are you do you have any?
Yeah, basically what happens that when we are actually, suppose we are moving in a valley, okay, and we might not be knowing that whether we have reached to the deepest point in that particular valley or not. Okay, because a deeper point might be there. Okay, so sometimes you might not be knowing this kind of that whether the particular function is having local optimality or not. Okay. So, and it is very difficult for you to identify using a derivative kind of optimization like gradient descent and all these things that which are also a group of exact kind of optimization. So there basically you can have a guarantee that you will be reaching to the valley or you can say the deepest point. But the thing is that when there are many valleys, okay, in a particular or some valleys in a particular valley, so there will be means after reaching a particular point, you will be finding that this is the deepest point, but there is a more deeper point than that particular point where you are staying in. So in those cases, these meta heuristics are very, very useful because if you are stuck in that particular deep, suppose point, it will throw you out from that particular point and you might start once again. Okay, so I think this way also it can be defended that when you should go for meta heuristics rather than exact kind of methods. Am I right, Shubham?
Yes, yes, sir.
Okay.
So I saw one or two hands more, but what I think is I should complete what I have in mind, and then we'll take some more questions.
Yes. Okay. Yes. So you can proceed. And what Professor you explained, I think you have that kind of slide also through some graph, correct?
Yes, sir. But it is not today. We will talk about that tomorrow.
Not today, but that will be explained because
yes,
this different values and yeah.
Okay, so where were we? We were talking about this linear programming example where we are talking about some constraints and we were modeling that problem, and now we are yet to write the objective function. So the objective function is to maximize the profit. The objective is to maximize the profit. So X is the quantity of product 1 and Y is the quantity of product 2, and profit from product 1 is 5 and profit from product 2 is 4. So we'll have 5X plus 4Y. And we are trying to maximize this profit, right? So it will be maximize profit. So this is the objective function such that this constraint and this constraint. Okay. So this is the mathematical formulation. I have written it appropriately. You can go back, use this slide and see. And I've also written the optimal solution. I have not mentioned how I obtained this optimal solution. So yeah, but this is the optimal solution to this problem. Integer programming problem. So for this integer programming problem, it is better to start with an example. Then only you will be able to understand the aspect of integer programming problem. But just to start, integer programming problem is a mathematical optimization technique where some or all variables are restricted to be integers. So in the previous problem, we saw that we used product as oil. So it could have been, it could have real values, 0.5, 1.5, and so on and so forth. But what if these were not oil? These were some product like a car or aircraft and so on and so forth. You cannot say 0.5 aircraft. So in such cases, we have to assume that the decision variables are integers, and that problem, when formulated, becomes an integer programming problem. Okay. So we'll see one example knapsack problem. Or what I should do is I will explain this knapsack problem in tomorrow's class, because I have to cover greedy heuristics. That is a problem specific heuristic. I will cover that and I will take the knapsack problem in the next class. Okay. So we will move on from this and we will talk about a greedy algorithm for a traveling salesman problem. So you see, we have seen traveling salesman problem, and a greedy algorithm is actually a, I cannot say problem specific heuristic, but it is an heuristic which can solve this problem. Yeah, but yeah, it is a problem specific heuristic which is designed to solve traveling salesman problem. So greedily, we will try to build that solution. So what do I mean by build the solution? So you see, for a traveling salesman problem, a solution can be represented as a set of cities. So you can say A, B, C, D, E, F for a 6-city problem. So this is one representation of a solution, right? What this greedy algorithm will do is, it is a construction heuristic. It builds the solution one at a time. So it will say, from city A, first I will visit, suppose city D. So it is building the solution. This is not a complete solution. It is building up the solution one at a time. So from city D, I will visit city E, and so on and so forth. And how it will select the next city? It will select it greedily. So one example of greedy algorithm for solving traveling salesman problem is nearest neighborhood algorithm. There are other greedy heuristics to solve TSP as well, but we are only talking about nearest neighbor algorithm. What is this algorithm? It is a very simple algorithm. Start from the initial city, select the city, select the city which is nearest to that city. So suppose you started with city A, select the city which is nearest. So suppose city D is the nearest. And then from city D, select the city which is nearest. So select city E, and so on and so forth until you cover all the cities. So this is a greedy algorithm to solve traveling salesman problem. I have given one example problem where there are 4 cities and we are starting with city A. And this matrix represents the distance from one city to the next. So from city A, if we visit city A again, the distance is 0. For city B, it is 10. For city C, it is 15. And for city D, it is 20. So starting from city A, city B is the closest. So A to B. Now A is gone, B is gone. From city B, you cannot go back to A because you have to visit other cities. You cannot go back to B because you have already went to B. Now from city C and city D, you see city D is the closest. Now you have come to city D, you cannot go back to city A, you cannot go back to city B, you cannot go back to city D. The remaining is city C. And from city C, you will go back to A. So this is how greedily you are building the solution. Okay. So this is a greedy algorithm to solve traveling salesman problem. It is a heuristic. It doesn't guarantee optimality. The solution can be bad as well. Okay. Limitation: greedy heuristic not always finds the optimal route. It may find a local optimal choice, but fails to minimize the total. I have not written it appropriately. It means that the greedy algorithm may find poor solutions. Okay, so that is the idea. And representation, I will cover this in the next class because from here single solution metaheuristic starts. Okay, so this is about greedy algorithm for traveling salesman problem. Just a minute, I'll discuss. So this was greedy algorithm for traveling salesman problem. One important problem is yet to be covered, which is known as the knapsack problem. From tomorrow's class, we will cover what a knapsack problem is, and we will cover a greedy algorithm to solve the knapsack problem. Okay, so these two things I did not cover in today's class. Now we can discuss. If you have questions, you can unmute yourself and discuss. Yes, Ajay. Yes, Ajay. So if you have any questions, you can ask me now.
Hello.
Yes, yes.
Sir, how you calculate the time in previous slide showed some time?
Sorry? Actually, there is some noise. I don't know who is. Oh, Ashutosh, are you asking?
I think Mr. Ajay has unmuted his microphone and is talking somewhere else.
No, sir. Actually, I'll mute the participant. Yes, yes, Ashutosh, I guess. Yes, Ashutosh. I'm not audible. Okay, please. This I don't know the name. Meta03. Please, can you speak?
Sir, am I audible?
Yes, yes.
Sir, how you calculate CT?
Ajay, I am muting. I am muting you. I am just mute you now. Please.
Shubham, once
Yes, sir.
you mute all, then whoever is having query, let him unmute because.
Sir, I have muted all, so I will just unmute one at a time. So, Meta 203, can you just speak up?
Yes, sir. Hello.
Yes, you are audible now.
Yes, sir. Sir, how you calculate the time in previous slide? You show some time, 2 CT, 3 CT.
Okay.
If CT and CT, it will be very difficult to calculate. Can I?
So I will just yes. So where we were discussing scalability problem of traveling salesman problem, right?
Yes,
This
sir.
one. So
Yes,
I was
sir.
saying, if you solve one, so if you have a solution, say this solution, and if you want to obtain the objective function of that solution, it takes 10 to the power minus 6 microseconds, 10 to the power minus 6 seconds, right? So if you have 10 cities, how many solutions you have? You have 9 factorial by 2. So these many 10 to the power minus 6 seconds you will take. So that comes out to be 0.18 seconds.
Okay, sir.
Okay.
Okay. Thank you so much, sir.
Yes, thank you. So Ajay, next, can you speak up? So Ajay, actually you are not audible. I can see you are unmuted, but you are not audible. So I will allow Sharans to speak. Yes, Sharans.
Sure. Hi, Shubham.
Ajay can share his query in WhatsApp. I can share what is his query. Yeah.
Yes, sir. Yes, Sharans.
So thank you for a wonderful session. Just a quick query. I wanted to ask that the greedy heuristic that we discussed, that you introduced today for that, in the end for the traveling salesman problem. So does that belongs to a class of meta heuristic, because we do have greedy heuristic for next step problems and others as well, or it's a heuristic only? Just
No,
that I wanted.
it is a problem specific heuristic. It is using the idea of that a city is close to another city, and if I visit another city and I complete the tour, maybe the overall distance is minimized. So it is a problem specific heuristic. If we go to the classification, for all the other participants, if you are getting late, you can leave the session now. Okay. So for this category, we are talking about that greedy heuristic belongs to problem specific heuristic, not meta heuristics. It is not applicable. So that nearest neighborhood algorithm is not applicable to knapsack problem or set covering problem or some other problem. It is only applicable to traveling salesman problem.
Okay, sure. Certain heuristic is applicable to multiple set of problems, then that comes under meta heuristic.
No, meta heuristic is actually a general purpose algorithm. You can apply it to many diverse form of. So you cannot just say ki if a heuristic is applicable to more than 2 or 3 classes of problem, it is a meta heuristics. No, it is still a heuristic.
Okay, so it has to be applicable to a much wider range of problems.
It has classifications. If you can, most of the meta heuristics are nature inspired. So I'll not say most of them. So if it has some parent or some grouping, then you will be able to realize that it is a meta heuristic. We'll discuss the classifications of meta heuristics maybe tomorrow. Yeah.
Sure. Thank you.
Yes. So I can see Zahara. Yes.
Yeah. Can you hear me?
Yes, you are audible.
Yeah, please. I have a scholarship with Prof. Dafal Mahata, starts at 9:30. Well, I have it clashes with your program at the last 30 minutes. Means I cannot attend the last 30 minutes and I cannot prove my attendance.
Okay, okay, no problem. So you can text Professor Sudeep and he will mark your attendance.
Okay, thank you.
No problem. Yeah.
Thank you.
I can see Siddharth has raised his hand many times. So do you have any query, Siddharth?
Yes, sir. Last one. Sir,
Yes.
please tell heuristic and meta-heuristic difference, sir. Please.
Okay, so heuristic is actually a parent class of meta-heuristics. So it is here itself. So heuristic is a parent class of meta-heuristics. It can be divided into a problem-specific heuristic or a general purpose algorithm, which can be applied to diverse algorithms. So just categorization. Heuristic is actually a subset of, meta-heuristic is a subset of heuristic. Okay.
Sir, can we say when search space is increases infinitely or very large, that is meta-heuristics?
No,
Can
no.
we say, sir?
When you are talking about search space, it is a property of the problem. Some problems can have a very large search space. Some problems can have a small search space. These meta-heuristics are a solution approach. It is an algorithm to solve that problem, right? Search space is the property of that problem.
Shubham, can we say the problem-specific heuristic is nothing but we are somehow providing additional information to the heuristic algorithm to generate the optimal solution?
So 2-3 quick corrections. We are actually not providing some additional information to heuristics. We are using that information to devise an algorithm to solve that problem.
Yes.
Okay. We can say extension of this, sir.
If you can give one example,
yes, sir,
then that will be
so greedy algorithm which you talked about, traveling salesman problem, is an heuristic. More specifically, it is a problem specific heuristic and not a meta heuristic. Right? Again, genetic algorithm is also a heuristic. More specifically, it is a meta heuristic. Okay. Right?
Yes, yes.
Okay, so Sheikh Muhammad. Sheikh?
Hi Shubham, can you hear me?
Yes, yeah.
Yeah. While we are applying meta heuristics for solving optimization problem, like there will be in the solution steps, such a space, there will be like many combinations will be there. Now, like, is there any particular sample size for the meta heuristics? Like, it will solve this number of times. Like, in this time, it should get like good optimal solution like that.
So what you are asking is if your search space is very large. So when we should use meta heuristics or not? So such doubt is there, right?
No, what I'm asking is like, for suppose if it is a large scale problem, if we apply meta heuristics we can't guarantee, right? Like whether it is a optimal or infeasible solution.
Yes.
How it's going to guarantee like how much how many what I'm saying is there will be some.
I have understood. So I'll answer the question. If you see if it is correct, then you can tell me. So what happens is when you're designing a meta heuristic, there is a step. That step is known as parameter tuning. In that step, you specify some properties of that meta heuristics. Like if you have a very large problem for genetic algorithm, you will specify that the population size, I don't know if you know about population size or not, but the population size is 100. Now for some other problem, you can increase the population size to 200, 300, 1000, right? So those decisions you are making to design the meta heuristics, and those decisions will help inform your meta heuristics to solve that particular problem. And how are you making those decisions? You have to perform some preliminary experiments, and those preliminary experiments are known as parameter tuning, and it is a very important step of before designing a meta heuristics. For some kind of problems, if your problem size is very large, while doing parameter tuning, you will realize that it is not a good algorithm meta heuristic to solve that problem. So that is the idea. There is not a perfect answer to this question. You have to test and then you will know, okay, it will work here or not.
Okay, Shubham, thanks.
Right. So Ajay, you are still raising your hand. you can unmute and we'll see if you're. Yes.
No. I think I have WhatsApp group where I got some clarification. It was related how the greedy model is different from the PERT CPM, which we have learned during our operational management course during the MBA.
Okay. So PERT CPM are actually, I have read it quite some time back. Professor Sandipan is here. Maybe he can help.
I only told him. It is basically kind of a problem-specific heuristic, you can call it.
Yeah,
And
I think
that is
three people have used. I think mostly it is used in the project planning, where if you see how to crash the timings and other things, also what are the best way to manage the project effectively and efficient manner.
Yes. So that is basically kind of problem-specific heuristic, and it is applicable to project network kind of, or network of activities kind of thing. It's where you are having this kind of precedence relationship and the activity times, okay, which are important parameters for the that particular problem. So there you can actually apply, but you can have linear program for that also. Okay, you can formulate a project network, means finding out the critical path. You can pose that problem as a linear program also, and you can use PERT CPM also. Okay, both will be leading to the this optimality.
Thank you very much, sir. Thank you. Great insight.
Thank you. So one time I can see that Zahra is again raising her hand. Do you have any doubt? Okay, so we'll conclude. Yes, sorry. Yes, go on.
No, I didn't raise my hand.
Okay. So your hand is actually still risen. Okay, no problem.
Okay, and just Shubham, just a minute. Whoever could not submit the attendance, can you please tell the registration ID here itself? You can unmute and just share your registration ID. If you are here and could not submit the attendance. Okay, yeah, Shubham, what you wanted to say?
What I was saying is, I couldn't complete the plan which I had for today's session. So only one part is remaining: discussion of knapsack problem and the greedy algorithm to solve that knapsack problem, and the limitations of greedy algorithm, because we saw traveling salesman problem and the greedy algorithm, but limitations can be visible for knapsack problem as well. So those three parts are left. I'll start tomorrow's class with that three parts, and then we'll proceed as planned for tomorrow. Okay. Thank you.
Thank you.
Thank you all the participants, and thank you, Shubham, also. I understand every one of us are very tired, students or faculty or other whoever have joined after entire day work we are attending. But without such motivation, it is difficult to learn something new tools also. Anyway, thank you, Shubham. Thank you all for your active participation. So we shall start tomorrow exactly at 5:30 p.m. And the way we have taken the attendance, it will be in the same way. No need to ask number of times that when shall we give the attendance, the link is not open. It will be in this mode. We'll be sharing new code. You have to write that code. And some of you are writing your registration ID in place of code. No problem. For today it is fine, but that is the code you have to write. Okay, that only will ensure that yes, you are only giving the attendance. That is the reason you are attending and you are only giving the attendance. There is nothing else. Okay, thank you all. Thank you very much.
Thank you. I'll end the meeting now. So yeah, good night.
Good night.